Hello everyone and welcome. Today we'll have a look into computer vision technology. We'll use artificial intelligence to process visual information, and we'll work on one of the many layers of security a vehicle has. But before getting into details, let me do a fast disclaimer. This system is extremely limited. Safety systems require extensive testing, redundancy, professional validation, and a suite of sensors working together. This video is designed purely as a demonstration of computer vision technology. Let's start with the first model, YOLO, which stands for You Only Look Once. YOLO is a deep learning model trained to detect all kinds of different objects. In this case, we will focus only on road-relevant objects such as cars, trucks, or people. This makes the system faster and more accurate. As you can see, here we have the object classes for detection. Each of these numbers is an index related with a specific object class. In this video, I'm using YOLO version 8. The N stands for nano, the smallest and fastest model. And.pt indicates the PyTorch format containing the neural network weights. Let's see this model in action. Notice how I'm using different colors for different vehicle types. This visual coding helps to quickly identify object types. While it's helpful for human interpretation, the model itself remains unaffected. The numbers at the top of the detection boxes are the confidence thresholds. In this case, I'm using 0.5, meaning we only trust detections that are at least 50% certain. Now we have object detection, but knowing there's a vehicle isn't enough. We need to know how far away it is. There are several strategies to measure distance, but since we're processing a single camera image, we need to use another deep learning model, MiDaS. MiDaS stands for Mixed Dataset for Monocular Depth Estimation. This model can estimate depth from a single 2D image. This model provides relative depth, not absolute distance. We can tell if something is close or far, but not if it's 10 meters or 50 meters away. Based on these values, I will use two classifications, normal or close. To reduce computational cost, I will use MiDaS Small, which resizes input to 384 by 384 pixels. While this sacrifices some detail, it's adequate for our demonstration. As we saw before, our system uses a threshold of 1200 to determine if something is close. But this is arbitrary and depends on camera positioning, lighting, and the specific scene. Not all detected objects are threats. A car 50 meters ahead isn't an immediate collision risk if we're driving at 30 kilometers per hour, but a car directly in front of you is. To assess this risk, I'm going to use something called region of interest. Let's assume that anything within a close distance from the frontal part of the vehicle is an imminent collision risk. This region will highly depend on the shape of the vehicle and camera position. The speed would be also a key factor to assess imminent collisions. The higher the speed, the larger would have to be our region of interest. Given our limitations for this video, and in order to keep these concepts simple, I'll use a 4x3 grid approach, focusing on the bottom middle squares as our region of interest, rather than implementing dynamic sizing based on speed and sensors. I'll create now a warning system with two levels, approach warnings and collision alerts. Approach warnings appear when vehicles are detected as close on either side, but only after they've been detected for 3 consecutive frames to reduce false alarms. Collision alerts are more serious. They only trigger when objects in the region of interest are detected for 2 or more consecutive frames. This persistence requirement prevents flickering alerts from single-frame detections. Here's the complete system working together. It's important to remember that real-world vehicle safety requires much more than a single camera. And that's it for today. As AI and computer vision continue advancing, these techniques will likely become valuable components in future automotive safety systems and self-driving technologies.